Hey guys, this is Professor Janacek. I want to go over an example where we find the volume of a solid of revolution. Remember, when doing these, the volume is equal to the area times the thickness. Now let's determine the volume of the solid obtained by rotating the region bounded by y equal to sine of x squared, y equal to 0, and x equal to the square root of pi over 2 about the y-axis. Now you'll see I've already graphed this. Just want to go over the graph real quick. Y equal to the sine of x squared is this line right here. Take your time when graphing that. It can be slightly challenging. Just best thing to do in this case is maybe to evaluate at some numbers, put some values in for x, see what you get for y. Should be fairly straightforward after that. Y equal to 0 is along the x-axis here. And x equal to the square root of pi over 2 is over here somewhere. It's a vertical line. Again, evaluating that y equal to sine x squared at this x value might help figure out where this all lies. And we are going about the the y-axis here. So you'll also notice that I have already selected a little bit here to analyze. I chose this little vertical bit just so you know you could have selected a piece going horizontally. It's really up to you. I really don't know which one to do. Initially, I try one, and if the integration works out nicely, I go with it. And if the integration doesn't work out nicely, then I try going the other direction. I do often try to go with a longer piece rather than a shorter piece. So if it's very obvious, if I have something, say, like this, I'm definitely going to pick a horizontal rather than a vertical. So go with something, go with a piece that's longer initially, and that will help typically. All right, so let's take a look. First off, we know we are revolving about the y-axis. And the piece we've selected is actually parallel to the y-axis. So let's see. Looks like we're going with that case, which means we will integrate with respect to x. And we will use that the area is equal to the length times width, although the length is the circumference, so I can change L to 2 pi r, circumference of the circle. By the way, this is known as the shell or cylinder method. Okay, so let's take a look at our volume. Remember, this is area times thickness. The area, I'll just use as A for now, but what is that thickness? Well, remember, that is dx. That's our differential. And in this case, we said we're going to use 2 pi r times the width for the area. Okay, so let's think about this for a bit. What is that radius? So going back to our diagram here, here's what the circle looks like. Again, there are many circles, but that's just an obvious one. And what is the radius of that circle? Well, that goes from the y-axis out to the edge. That is actually an x value. So our radius in this situation is equal to x. What about the width? Now the width is going to be the width of our little piece that we've selected to analyze, and that is the difference of the two functions. So our width in this situation would be the top bit here, this top function minus this bottom function. So that's sine of x squared minus 0, which is really just sine of x squared. So I think we're ready to put things together. We are integrating with respect to x. If you look at those x values go from 0 to square root of pi over 2. And then we have 2 pi times our radius, which we've already determined was x, times the width, which is sine of x squared minus 0. I don't need to write that minus 0 in there. And then, of course, we have dx. And there we go. Our integral is set up, ready for us to work. Let's see. I'm going to do a couple things. I'm going to start by factoring out the 2 pi. That's a constant. And looks like I'm going to need to use u substitution, so I'm going to move this x here to the back. So commuted things just a little bit. Okay, so for u substitution, in this case, I will let u equal to x squared. That means du would be 2x dx. Oh, okay, so I see that I have x dx. I just need the 2. So what I'm going to do is I'm going to go ahead and bring that 2 from the coefficient back inside. And put it back there with the x dx. So now it's looking pretty good. I think I'm almost ready to perform this substitution, although I need to change those limits of integration. I'm starting with x equal to 0. When x is equal to 0, then u is equal to 0 squared, which is just 0. And for x equal to the square root of pi over 2, u is equal to the square root of pi over 2 squared, which is just pi over 2. So our limits of integration have changed now from 0 to pi over 2. And I'm also going to change from x's to u's. Remember that u is equal to x squared and du is equal to 2x dx, so I end up with the sign of u du. Oh, well, isn't that going to be nice to integrate? No problems here. We're going to integrate sine of u. That gives us negative cosine u. And we're going to evaluate that from 0 to pi over 2. Yes, we still have that pi in the front. Don't forget about that. All right. Also, watch that negative. A lot of times people will forget about that. Remember, we're integrating, not differentiating. So let's see. This is really just negative pi cosine of u evaluated from 0 to pi over 2, which gives us negative pi times the cosine of pi over 2 minus negative pi cosine of 0, which is negative pi. Well, you can simplify all of that. All in all, you should end up with just pi. So there we go. Remember, this volume does not have any units. If it did have units, it would be the units cubed. Enjoy!